using kinetic theory, right? So the whole point of dragging you through this was to show you that if we run this little model, we find out that we need to have that average value of Vx that we can get from the kinetic theory of gases, or from the Boltzmann distribution. We need that average x to end up calculating the pressure. And you'll see that things end up fitting together quite nicely. We don't like to speak just in terms of velocity in x, y, or z directions. We like to use that vector velocity. If you take a look at the average value of v squared, it's going to be equal to the average value of v of x squared, the average value of vy squared, average value of vz squared. Statistically, there won't be a preference to move in the x, y, or z direction, so these average values will all be the same. So you could say that average value of v squared is equal to 3 times the average value of vx squared. So vx squared is 1/3 times the average value of the vector velocity. Plug this back into our expression for the pressure, and you get that P is equal to n times vector velocity, average value of vector velocity squared, divided by 3v. This is an equation in your text, equation 1.11. Even though the text and I don't do everything the same, I really want you guys to read through that text at least once. For me, I do it 3 or 4 times, or 3 times. Read through it once, then I'd come to my lecture, I'd read through my notes, and then I'd go read through the text one more time after that. So, we calculated earlier from the Boltzmann distribution that the average value of v squared was 3 kT over m. You plug that guy into your average pressure expression, and you get that average pressure is n times Avogadro's number times k. It turns out that Avogadro's number times k is simply r, the universal gas constant, and times T over volume. And this is starting to look like an equation we're all very familiar with, the ideal gas equation. Yeah? Are you guys impressed that we just used the statistical treatment and we were able to derive the ideal gas expression? We had a couple people shaking their head. Why aren't you impressed?
I'd rather just jump to this one.
You would have rather what?
Just jump straight to this one.
I'm fine with people giving me answers. So I'm afraid of
I thought it was pretty neat. There's a couple reasons it's not quite as neat as I'm just trying to sell you on, but it is a pretty neat result, right? We can use this kinetic theory and we can get back what we know about ideal gases. Now, the thing that I'm not telling you is that it's the thing that I'm not telling you. The thing that I'm not telling you is the thing I'm not telling you. I was deciding when not to tell you, but I thought, oh, maybe that would just get confusing. Turns out the ideal gas theory was used to develop the form of the Boltzmann distribution that we formed, or that we utilized, and so it's kind of circular logic, but it ends up being that it works not just for gas systems, transition energy of gas systems, it works for other systems as well. But we're able to get back our ideal gas law from our kinetic theory. There's a little proof that your book does. What time do we go till? Till 50? So I got like 5 minutes left. Yeah, so you can use the known behavior of ideal gases. If you rearrange that equation that we have up here, you can say that P times Nm VRMS over 3 times the volume. Move the volume up to the P, you get PV is equal to something, Nm times VRMS squared over 3. And from the ideal gas theory, that's equal to nRT, PV is equal to nRT. And plugging that in and solving for VRMS squared, you get back 3 kT over m. So work the logic in the reverse direction, it works out that way as well. That little proof was in your text. I think this is going to be the last thing that we say about this for the day. Once we get back here on Thursday, we'll get into when this doesn't work and why it doesn't work. This, we probably, well, we will use this. We'll use this little piece. There's a relationship between the kinetic energy and the velocities. We already know that. We knew it because when we took the Boltzmann distribution, we plugged in 1/2 mv squared, replaced the kinetic energy with that. But this is just demonstrating that you can recast the root mean square speed in terms of the average kinetic energy. You don't have to cast it in terms of those other. Anyway, yeah, there's a relationship between the kinetic energy and the velocity, and that's your equation. This is what my brain is on. This guy is a rearrangement of the velocity distribution, plugging back in the kinetic energies, the total energies of the system. And so this recasts the probability distribution in terms of the energies instead of the velocities. And you'll notice that the exponential dependence on energy and the exponential dependence on velocity in the equations changes. So the Boltzmann distribution takes on a new form when you're looking at absolute energies. Don't worry about that. I just want to show you that you could recast it. I'm not going to give you any problems using this. But take a look at this one. Right? Take a look at that kinetic energy term. Now, I'm going to have your first homework assignment posted tonight. I'll email it out to you all if you don't get it from me. There's probably a problem with your email address, that I don't have the right email address for everyone. I think there's a couple out there where the email's not working. So if you don't hear from me tonight, email me. The homework will be posted, and I'll get the set notes out there for you. Yeah.
What is the homework due?
One more time?
What is the homework due?
You know, I'm kind of, I got so many things going on at the same time. I'm kind of doing things by the seat of my pants a little bit. Generally, a homework assignment will be due about a week and a half after I assign it. I'm not going to be going crazy on homework this time through. I just don't have the time for it. The homework is mostly for you. It's mostly for practice. And one of the things that clubs live in daylights out of me when I was an undergrad is I'd go to classes and they'd hand me a homework assignment and I'd start working on it and I wouldn't get it done by the deadline. But I'd be working on it. It would be, important to me. And so I'd keep it in my pocket and I wouldn't turn it in by the due date. And then eventually I'd get it done and I'd hand it in and I'd have all the problems right, because I took my time with it. And some instructor would hand me no credit because I didn't make it by the deadline. It never made any sense to me that you could do better work than someone else, but it just wasn't done, as timely as theirs was, and so you receive less credit for a better product. But that's part of America and the world of capitalism. Anyway, the reason for that whole rant was mostly the homework is for you. So take it home, work on it until you're done. Take your time. But if you show me that you're doing good work, if you're doing hard work, that's what's most important to me, because it's what's most important to you, right? So don't worry about due dates and homework so much, just get it done.